We go on our last set of notes for chapter 6. So we're looking at velocity, relative velocity of two planes for this example. So we've got plane Q and plane C, and we're trying to find out what's the velocity of plane C relative to plane Q. So picture yourself, you're sitting on plane Q, you're looking out the window at plane C. What does plane C appear to be doing? Okay, so that's what the question's asking us to do. So let's start off with what these directions look like, these velocity directions look like. So we've got velocity of Q is going due west at 450 kilometers per hour, and plane Q is on a bearing of 210 degrees at 540. And so we're trying to find the velocity of plane C relative to plane Q. Okay, so plane C relative to plane Q, and we use V because we're looking at velocity rather than position. And we know now from our previous questions that if we're doing C relative to Q, or velocity of C relative to Q, it's going to be positive C, negative Q. Now go back and have a look at the previous questions or the introduction to the book if you're still not sure exactly why we do that. But I guess a little quick explanation is what we're actually doing is by taking away Q, we're kind of making Q stand still. So we're going, well, if that's what Q is doing, if we do the opposite of that, we get back to the initial position of Q. So we're pretending that that's exactly standing still and then putting that relativity onto C. So we're effectively stopping Q and then seeing, well, what does it appear that C does if we stop Q? Okay, so one way of thinking about it. All right, so what would this look like if we now draw a positive C and a negative Q? So there's my positive C, so still looking exactly the same. But now we're reversing Q. So Q's going in the opposite direction. And then this is going to give us our resultant, our C relative to Q direction. Okay. So let's put in the angles that we know. So we know we had 210 degrees. So obviously revolution adds to 360. So that's going to be 150. We've got co-interior angle, so that's going to give us 30, and then because that was due west, that's a beautiful 90 degree angle, so we know that's going to be 60. So we can just use the cosine rule for this. So we know we've got the two side lengths and the angle in between is 60, so we can throw that straight into our class pad and get a resulting velocity of 501.1 kilometers per hour. So that's, we've now found from velocity of C relative to Q. So if you're looking at C from Q, it appears that it's traveling at a speed of 501.1 kilometers per hour. Now remember from Despicable Me though, vector has to have direction and magnitude. We have our magnitude, we need our direction. So we're going to find theta here, and once we've found that, we can obviously work out from our 210, or however you want to work it out, we can work out our bearing. So using the cosine rule again, obviously you could use the sine rule as well, but sometimes cosine rule is nice because you don't have to think about your other options if there is one. So throw that all in, we get our angle is 51.1. and the bearing then becomes 158.9 degrees. And again, always check that the angle that you finish off with makes sense. We can see that it is less than 180 degrees, but definitely greater than 90, so just check. Obviously your diagram might always be perfectly to scale, but you should be getting a rough idea of where you should be heading, so you should usually be in the right quadrant, unless it's one of those tricky ones where you're right on an edge. So think about what this is asking. So remember, whenever we're given a worded question, it's good to give a worded explanation of what we're seeing. So it says, what is the velocity of plane C relative to Q? So we've said the velocity is 501. We've said the direction is 158.9. So what this actually means is if you're on plane Q, plane C would be traveling away from you at a bearing of 158 degrees, and it would be traveling away at 501 kilometers per hour. Okay, so that's what that actually means. All right, example 3. So we've got a person riding a bike at a constant speed of 12 kilometers per hour. And now we've got the wind impacting them. So this, think back to when we did our winds and tides investigation. So this all links beautifully into that. So how is this wind? So rather than the wind pushing him, it says the wind is actually appears to be coming from the north, but obviously he's traveling towards it at his own speed. Well, not towards it, but he's traveling as well. So how could we work out what the true velocity of the wind is if we can see that it appears to come directly from the north? All right, so let's start off with the person 12 kilometers per hour on a bearing of 70, okay? And then it says that the wind appears to come from the north. Now remember, when you're doing these, coming from the north means it's actually going south. So just always be careful when it says coming from the north, it means the opposite of what you expect. So always be careful when you're talking about wind. So the wind is coming from the north, and remember that's what it appears to be doing. So that's the wind's velocity relative to the bike rider, and it appears to be coming with a speed of 9 kilometers. So we want to find the true velocity of the wind. So this obviously is using a situation where we're working backwards. So we know the wind relative to the bike rider should be the wind take the bike. And so if we rearrange that, because we obviously want to put it in the form of what we're trying to find, so that must mean the actual velocity of the wind is going to be the relative velocity of the winds according to the bike plus the bike. So let's draw that diagram. So we want both positives this time, so positive 9, positive 12. Again, make sure you've got that nose to tail though. What angle do we know? So this was beautiful directly down, and that's going to be the same angle there. So that's going to be 70 degrees in here, and then our result, our actual velocity of the wind is what we're trying to find. So cosine rule again. Put everything in that we know, and we get the magnitude is 12.3 kilometers per hour. Again, we need the bearing too though, so we want to find this bit up here. So let's find theta, and then all we have to do is take that away from 180. Put that in our cosine rule again, and we get 66.5. Okay. So the wind is coming from, and again, so remember, coming from is where we have to be careful with the wind. So this was the bearing, but that means it's actually coming from all over here. So we have to say it's coming from 293.5 degrees. Okay. Okay. Example 4. So to the pilot of a bomber aircraft traveling with velocity, so we use it back to components now, so 150i 200j, a fighter aircraft appears to have a velocity of 209 440j. Find the speed and the bearing of the fighter aircraft. So as we've worked out already, it's actually usually a lot nicer to be given component vectors, as it's easier to add our i's and j's rather than trying to work out cosine rules and angles and things like that. So it's nice to be given a question like this. So we've got our velocity of b, and we've got, oh sorry, that was the wrong order. Now we've got f's velocity relative to b, so it says appears. Okay, so remember that means it seems like that's what's happening, but it's not the true velocity, it's the relative velocity. We want to find the true velocity of f. And so think about what we know. So f relative to b is going to be the true velocity of f. Take the true velocity of b. Rearrange into what we're actually trying to find. So again, we've got both positives for those. Then we can put them in. The best thing about component vectors, we don't need a diagram because we've just got our i's and j's. We don't have to worry about where angles are and things like that. And we can simplify to get the true velocity of s is 350 and 240. We know the speed then is just going to be the magnitude, which gives us 424.4. And now just remember, because these are both positives, they are going to be in the first quadrant. But if you're ever going, oh, what's actually happening there, it is a good idea to draw a quick sketch. But they are both positives, so we know they're both in the first quadrant. So if you get an angle greater than 90, or if you get an angle greater than 90, you know you've done something a bit wrong. But let's just quickly do that sketch. And so we can see the bearing would be 55.6 degrees. Okay. All right, one more example, guys. The next one goes over a couple of slides, and then we are done, and that's all you need for chapter 6. So lucky last example. Example 4 again. I meant to say example 5. All right, we've got Katie is traveling on a bearing of 70 degrees and a speed of 70 kilometers per hour, and sees Taj appearing to travel at a speed of 90 kilometers per hour. Taj later said that he was actually traveling at a speed of 110. So find the velocity vector for Taj. All right. So we're looking for Taj's actual velocity. And because we don't know the direction of either of Taj's vectors, let's actually change it into components, because we know components are actually nicer to play with. Okay. So let's let the velocity of t equal some value of I and some value of b. His speed was actually 110. So that must mean the magnitude of those two values without the square root is going to be the same as 110 squared, isn't it? Okay, so we know that must be true. If we were to change Katie into component form, which we can do, we know Katie is going to be 70 cos 70 and 70 sine 70. Draw a sketch. If you're not confident where these numbers came from, think about what that would look like and draw it, because you want to always be really sure that you're happy with your sines and your coses and your angles and the positives. Okay, so draw it if you're not feeling confident. So if we work those values up, we get 65 and 23. All right, so now hopefully we're starting to get enough information to get where we need to go. So we know the velocity of t relative to k is positive t, negative k. So we know we've got A and B take 65.778 and 23.941. All right, now we've got, sorry, my dog is distracting me. Now we've got our next slide. So we know our magnitude of t relative to k was 90, so we're given that in the original question. So Katie thought that when Taj was coming towards her, the relative speed was 90. So we know that the relative magnitude, we've got our I component squared, so the difference between our I component squared, the difference between our B component squared, so you can probably hear my dog in the background. And now we have enough information to solve simultaneously, okay? So we've got A and B. Sometimes your calculator won't like it in particular form, so just keep in mind that if that ever happens, if you put in your two equation, your calculator just gives you the spinning wheel of death and you just think, why doesn't it like that? What you can actually try is substitute one into the other. So rather than having your a squared plus b squared equaled 12,100, we can actually go, well, what would that look like as a? So we know that that's what that would look like as a, and actually just put it into the equation. So let's just replace that with our a, so that we just have one variable now that we're trying to solve for, and then you can put that straight into main. Okay, so just keep in mind, if simultaneous doesn't work, just play around with your calculator. Usually we'll get there if you just give it a little bit more help. And then we can solve. So we can solve for B, substitute back in to get it for A. And then finally we should get that the solution for the velocity of t is 29.0 and 106.1 in component vectors, or because we didn't have any directions, he could have actually been coming from a slightly different direction. So both of those solutions work. So if you're ever unsure, draw a sketch, check to see if it actually would make sense in both. But because we have these squared values, remember there is possible to have two solutions. Okay, so give it a quick sketch if you're not sure. All right, guys, enjoy chapter 6. Thanks.